So what we want to do here is actually I'm going to walk you through step by step the analysis using the well, first, because I started shooting the video before my mic stopped working, so hopefully that won't happen this time, but I'll walk you through how we get this data. Okay, so first things first is I've already tracked them as pretty linear, and then the slopes slightly changes, right? The slope slightly adjusts. And if I look at mass B, then we just have this data here. Okay, so what I've done is I've imported sets of data, pardon me, into Excel, and I'm just going to look at mass A, right? And the reason being, okay, if we come back up here, the idea behind this lab is to show that momentum is conserved, that mass times velocity is conserved under the condition that the only forces that act in the system are internal to the system. So what we mean by that in this case is the carts are colliding. The carts are going to be putting forces on each other. So as long as we consider both carts as part of the system, then those forces that they put on each other are going to be internal forces to the system. There's not something external, like a third force, that's pushing on both carts as they're pushing on each other. Something of that nature. Pardon me. And so, in the momentum 3 case, the third video, we call an inelastic collision because the masses stick together. So in general, right, M1 M2V2I equals M1 V1F plus M2 V2F. So that is the specific equation for momentum conservation between two objects that are colliding. And if one of the carts, in this case cart 2, is stationary, then I can neglect it from the original term. And if the carts stick together, then the velocity is going to be common, so I can factor the velocity out and I get this. So this is the equation that we want to compare. What is the initial momentum, the momentum of the first cart before the collision, compared to the momentum of both carts moving together after the collision, right? Now, in this video, right, carts are approximately 1/4 of a kilogram, or 250 grams, and mass 2 also has a 250 gram mass on top. So M1 is going to be 1/2 of a kilogram, or 0.5 kilograms. Okay. So I come back up here to the data that I've exported, and here's the entire path of cart 1, and you'll notice that the collision happens right around in here. So I want to take, all right, and that's what I've done right here. Okay, I've taken up to about 0.25 seconds, which is going to be about right here. So this data point right here. Right here is my last data point. Okay, that just made it fuzzy. So from here to here are the data that are right here. And I've plotted these and I've fit it with a trend line. And remember that the trend line is the velocity, right? The slope of a position versus time is the velocity. So my velocity on part 1 is 0.4849. So that is the value. The initial momentum of the first cart can be calculated by taking 0.4849 and multiplying it by 1/2 a kilogram, right? So this times this. And if we do that, you get this, okay? If we do that, you get this. So then the next thing to do is to calculate what the final velocity is. So what I'm going to do is I'm going to take from about 0.0 seconds and onward, because that's safely after the collision. And so if I do that, I'm going to select these data. I'm going to select these data right here. Oh my goodness. Okay. One more time. There we go. And I'm going to display the slope or the trend looks. This will actually turn out to be a smaller trend line. Okay. It's just the way that Excel formats it that it looks funny. And so doing that, I get 0.3173. Okay. So that is the slope of the carts after the collision, 0.3173. And so that is the velocity, that is the velocity of the carts after the collision. So now the final momentum can be calculated, right? The final momentum can be calculated because the final momentum is just the sum of the two, 0.75 multiplied by 173. And that gives you a final momentum of 2380. Okay, 0.2380. And so now this percent difference, all right, is comparing your initial momentum to the final momentum, right? 0.24245 compared to 0.2380. And this is actually pretty good, right? This is actually pretty good because this is kind of like the difference between $24.25 versus $23.80. Okay, so it's really not that different. But once again, how did we get this percent difference calculation? So the percent difference, if I look at my two values, I've just imported these two numbers into Excel. Percent difference is the difference between the two numbers, absolute valued, so I don't have any negative signs, and then divided by the average. So what I've done, I've taken the difference between the two, and I've just made sure to take the larger one and then subtract the smaller one from it, so I always am positive. And then dividing that by the average for me, okay? So I take the difference between my two numbers, divide by the average, and then multiply that by 100 to put it on a percent. And my result is 1.85%. So what this is saying is that momentum is conserved in this case to within 2%. That's pretty good, right? That's actually pretty good. Now, a lot of you are confused with the uncertainties on the slopes of the velocities. So let me show you how we get those pretty quickly using the Inelastic function. Highlight 2 columns and about 5 rows, and then type in linest and open parentheses equals linest open parentheses, and now you'll see that it wants the known y values first. So I'm going to come up here and I'm going to highlight the known down to that data point right there, and then it wants the x values, and I'm going to highlight no, shoot, what happened? Not sure. Let me try that again. Equals linest open parenthesis, and it wants my y values. Set that, and then I'm going to hit comma, and it wants the x values, so we'll do the same thing, comma. Now these two numbers, your constant and stats, just put ones, so 1, 1, close parenthesis, and Control-Shift, Enter, right? And once you do that, 0.484864, which rounded up to 4 decimals is 4849, as reflected right here. The intercept is negative 0.2616, or rounded to 3 decimals is 0.262. So this number represents the uncertainty on this slope. Okay, so what you can think of this as 0.4849 plus or minus 0.0037. So that's the number that goes here in this sigma box right, 0.0037. Now, what does this represent? Okay, this represents a way to try and determine if the two momenta, if their error bars overlap. This is essentially an error bar. Okay, this is essentially an error bar. And if you do a linest function on the final slope, right, on the data down, you'll find that here is given by, oh, no, I want open parenthesis, not 9, open parenthesis, 1, comma 1, close parenthesis, Control-Shift, Enter. Okay, so Here is 0.3173 plus or minus 0.0040. Okay, so that's where this sigma comes from. So these are just your uncertainties on your slopes. These are just your plus and minuses. And the point of putting them in is to try and determine, do your momenta overlap? Okay, you can't just use 0.238 plus or minus 0.004 and say that that doesn't overlap with 0.4849 plus or minus 0.0037. Okay, because what we actually really wanted to compare are the momentas, not just the velocities. But these give you a way to try and determine the quality of your slopes. Okay, so the higher the quality of your slope, the less noise and the less scatter that's in your slope, the smaller those uncertainties are going to be, right? And so really these are just a way to qualify, or actually quantify rather, the quality of your slopes. Okay, and these should be pretty small compared to these, right? Your uncertainties should be pretty small compared to these. With really good linear trends, these uncertainties should be really, really small, right? Is that number one, your slope is rather linear, the uncertainty also, and number two, that you probably aren't going to have your error bars overlap if you actually calculate the uncertainty on PI and PF. If you calculate those uncertainties, and there's a way that you beyond what we need to do here, but what this is telling you is that those error bars actually probably aren't going to overlap, and that's because the ratio of how small this is compared to how this is, how large this is going to be a much smaller amount than 1.85%. Okay, so these momenta, that percent is still larger than the amount that the slopes, the uncertainties on your slopes contain. Okay, so don't wrapped up in those uncertainties. Okay, just calculate them using the linest if you can. But what we're really concerned is the here. Okay, this is the major result. What are the percent differences between your momenta before the collision and then after the collision? Okay, that is what we're really after. So I hope that clears some things up, and hopefully you will find that useful and beneficial. If you guys do have any further questions, please let me know, but I hope that's been beneficial for you. All right, we'll see you next time.